The purpose of this video is to illustrate the concept of thermodynamic equilibrium. When quantum mechanical effects can be neglected, the probability distribution of particles' coordinates are determined exclusively by the potential energy. The form of the distribution is credited to physicists Boltzmann and Gibbs. Here we consider a set of 1,000 particles, each confined to a box of height h, and performing random Brownian motions up and down in the field of Earth's gravity. A small subset of these Brownian particles is shown in the top left panel. In the top middle panel, we histogram the altitudes of the particles, whereby we break up the total altitude range in a set of 13 horizontal slabs of equal thickness. The smooth line in the same panel shows the Gibbs-Boltzmann prescription for how tall the histogram bar should be. The relationship between the potential energy and the corresponding probability is simple. The probability decreases exponentially with the energy. The rate of decrease provided by the inverse of the characteristic thermal scale kBT. Kb is the Boltzmann constant and T is temperature. The formula for the distribution is provided under the video. We also observe that in equilibrium, the number of particles at each altitude fluctuates around a steady value that depends on the altitude itself. These fluctuations directly evidence that thermodynamic equilibrium is in fact dynamic, as the name suggests. The top right panel shows the dependence of the potential energy on the altitude. The green horizontal line indicates the altitude L, which the potential energy of the particle is equal to the characteristic thermal energy scale, kBT. The altitude L thus reflects how high a particle can typically reach at a given temperature. We see the probability distribution decays with altitude at the rate given by the inverse of the length L. Brownian motions can be accurately modeled using the Monte Carlo algorithm, which we are employing here. Next, we illustrate how thermal equilibrium is established. For the sake of concreteness, we first place all of the particles close to midway between the bottom and top of the box and subsequently allow the particles to perform Brownian motions. We observe that over time, the system approaches the equilibrium Gibbs-Boltzmann distribution for the particles' altitudes. As a quantitative measure of the approach of the system to equilibrium, we show in the bottom panel the time dependence of the Gibbs entropy. The formula for the entropy is provided under the video. Consistent with the second law of thermodynamics, the Gibbs entropy typically increases with time if the system was initially prepared away from equilibrium. We observe that in equilibrium the entropy fluctuates around a steady value, the amount of fluctuation decreasing for larger systems. Next, we show the same setup as in the preceding illustration, but with the total particle number increased by a factor of 100. According to Gibbs' notion, that particle occupying an individual slab can be thought of as a standalone ideal gas. The fluctuation of the bar height while in equilibrium should decrease by a factor numerically equal to the square root of 100, which is equal to 10. Likewise, the entropy fluctuations in equilibrium decrease by a factor of 10. Next, we lower the temperature and thus decrease the amount of energy typically available to a particle. We see that as a result, the particles huddle closer to the bottom of the box when equilibrium is established. This corresponds to a relatively small value of the length L. In the extreme limit of vanishing temperature, the particles would simply all collect at the bottom of the box. The low temperature limit explicates that the thickness of the atmosphere of a planet is essentially determined by how high a molecule can jump off the ground at a given temperature. Note that for the sake of time we have accelerated the movie because equilibration becomes progressively slower as temperature is lowered. Finally, we consider the opposite limit of high temperatures, so high that the length L is now significantly greater than the height of the box h. Under these circumstances, particles are almost evenly distributed among the slabs because there are 13 slabs. A particle can have 13 distinct configurations of a comparable likelihood. Consequently, the equilibrium entropy per particle becomes numerically close to log 13 times the Boltzmann constant, which is the simplest realization of Boltzmann's celebrated expression for the entropy.